Now let's continue with our discussion of heating and cooling problems by looking at two of the problems that you're having to solve for homework, just in terms of how to set them up and interpret them. Let's at number 3 of your homework, where here we're looking at taking a pot of boiling water and pulling it off the stove and then seeing how the water in that hot water actually is going to cool off through time. So if we let capital T, little t, equal, in this case, the temperature of the water in the pot, and it's not only that, it's the temperature of the water in the pot after, let's say, little t minutes. So it's very important to keep in mind what the time unit is. So after t minutes, we're interested in what the temperature of the water has reduced to. So you've initially heated it up boiling, so you're actually given in this case that the initial condition T of 0 is 100, and of course we're looking at degrees Celsius. But also you're given that after 6 seconds it's actually cooled down, and it's cooled down to 80 degrees. So that could be very, very helpful in terms of resolving what the differential equation is going to be specifically for this particular problem. So we go back to Newton's law of cooling. Which states that the rate of change of temperature is proportional to the difference of outside or the environment. It's proportional to the difference between your inside temperature and outside temperature. That could be written in this form. K is the constant, the time constant in particular, times m of t minus the quantity capital T of little t. And we're looking at the particular case that the kitchen temperature, which reflects the outside temperature outside of that pot, in this case is 20 degrees. So this is actually 20. That's the kitchen temperature, and it's assumed to be constant. So that would be known. The only thing that we wouldn't know at this point would be this particular quantity, the constant K. But you can use the other condition that you know that 6 minutes later it's reduced to 80 degrees to find K. But you will do that after you solve for T of t from the differential equation, which in this case will be separable. So you're going to solve this, treat the K as a constant. You know this is now K times quantity 20 minus T. Solve that separable equation. Then use this condition T of 6 equals 80 to find the particular K value. All right? And then you will have everything set up to be able to finish the problem, which would be that you would be able to, again, find the exact form for T of t, use this particular condition T of 6 equal to 80 to find K, so that you'll have T of t in part B of that problem fully defined, and then in the C part all you need to do is basically set that solution T of t. So in part C, which you'll need to do, the question is to find the time that it takes for the temperature to reach 40, so whatever solution you get for T of t, set that equal to 40, and solve for T minutes. Okay. So that's pretty much, again, part B is just to solve for the solution. That's part B. Again, you'll need to find the K using this other condition, and that should be pretty much all set for you. Number 4 is an interesting problem because it's a little bit different. It changes the model a little bit because we're looking at the temperature inside of a van or a car. And there's air conditioning and there's a thermostat. And of course, whatever that thermostat is set to determines how much cooling you're going to be doing at a given time. So let's look at this carefully. Number 4 is a little bit of variation of what we just had. Here, the temperature, capital T of T, is the temperature inside the van. Again, we're always looking at temperature inside a building, a van, water inside of a pot, whatever. So that's the convention here. So we're looking at that temperature inside the van after little t hours. So it's important to know there is a difference in this time unit. T is now in hours. The new model you're looking at is that the derivative is not only just Newton's heating law of cooling, which is this component, the outside temperature outside the van minus the inside temperature inside the van, perhaps plus any human factors, people getting in the car and so forth, if we take that into account. But now you have a thermostat and you're actually running AC, so in this case it'll be the difference in the temperature that you've desired or set the thermostat at minus the inside temperature. So again, depending upon how warm it gets, that will add a new component because the air conditioning will come on. So these are two constants that will come into play in this particular model. But you're given, if you think of them sort of like time constants, they've actually given you the fact that 1 over k is equal to 2 hours. So that actually corresponds to the fact that that's sort of, you're going to see a significant change inside the van's temperature of 2 hours in time. Similarly, they gave you the fact that time constant for 1 over k, again, this was with respect to the van and the outside. 1 over k they gave you as 1/3 hours, which reflects the time constant for a van with air conditioning. In other words, it doesn't take nearly as long to detect a significant change in the air temperature in the van when the air conditioning's on. And we all know that once you turn the air conditioning on, it doesn't take very long for you to feel the difference. So that's sort of consistent there. And so now we have this model where you're looking at an influence of the outside and you're looking at the influence with respect to turning the air conditioning on. And the relationship between these constants, which was given to you, is that K1 is equal to K plus Ku. Okay, all right? And of course now you knew that K is equal to 1 over K is 2, and you know that 1 over K1 is 1/3. So that would just say that 3 has to be 2, it has to be 1/2 plus Ku. So we've already figured out now that the Ku constant must be equal to 3 minus 1/2, which is 5/2. Okay. So we almost have all the components now. We know what the K is, we know what the Ku is. For this particular problem, we're going to ignore any effects of humans, so you'll take that term to be 0. All right. And we're also going to assume that the outside temperature outside the van is constant at 80. So again, that's constant. Okay. So again, what do we know now? Now you know M, you know K, you know Ku. You're setting the thermostat, according to the problem, you're setting it at 68 degrees, so that stays at 68. Push that up a little again. So you almost have all the components there. You do have all the components now. You can fill out all of these terms based on this data that you're given, all right? And then what you're doing in part A of this particular problem is to construct a linear differential equation. Okay. All right? And not only with that, you'll have the initial condition, so it's going to be an IVP problem because you're going to have the initial condition that initially the inside temperature of the van has heated up to 125 degrees. Ouch. So that's going to be the initial condition. And then having done that, then in the B part, you would be then solving the IVP. Associated with the linear differential equation with that initial condition. And then finally, in the part C, all you're asked to do is to find out, well, how long is it going to take for that temperature inside the band reach to fall down to 75 degrees. So you'll take your solution that you're going to determine from part B, set it equal to 75, solve for that temperature in hours, and then, of course, convert that final answer to minutes by just multiplying by 60. Okay, so whatever you get for hours, just multiply by 60. So that should set you up fairly nicely to be able to take a little bit of a change in the model from Newton's law of cooling because of the fact of using air conditioning with the thermostat. So, so you should now be fully able to solve both problem 3 with this particular model, a very simple model, Newton's law of cooling, and then problem 4, where you have a more sophisticated model take into account a thermostat control.